Well, so here's an example from chapter 6, doing the method of joints. So just as kind of a quick overview, here's the steps that you need to solve for method of joints. You're going to find global equilibrium. You got to do that first. You can do that with the entire truss. Then you look for any zero force members. Then you draw a free body diagram. You pick a joint to start with. Remember, you can't have more than two unknowns because it's now particle or point equilibrium. So all you have is the sum of the forces in the x direction, the sum of the forces in the y direction, and you solve. And you continue to solve until you have all the unknown members. So here's the example. It's similar to the one that Dr. Hansen does in one of his videos. However, I've got actually the whole entire solution here. He doesn't actually do the whole solution out. So feel free to watch both videos, both mine and his, because you'll get the whole problem if you go through both of them. So in this particular example, you got this big truss. It's loaded with two 10 kilonewton and 120 kilonewton force, and you have a pin on one end and a roller on the other end. It looks it looks essentially impossible because you've got all these joints, right? What makes this problem a lot easier than it looks is the fact that it's symmetrical. So it's loaded symmetrically, and the truss itself is symmetrical. So everything on the right side is equal to everything on the left side. So for instance, KD and DI, they're the same. They're going to have the same force on them. So that makes things easy. So remember, step one was to find global equilibrium. Well, again, because it's symmetrical, right, the force will be split between the two supports, the A and the G. Now, there's an AX and an AY. Well, nothing is in the X direction, so AX equals 0. Right? AY and GY are going to be split half and half. So you've got 40 kilonewtons, there's 20 on each. Finding the zero force members. Well, I mentioned this in the other video, so here's kind of a graphic explanation of it. 1 and 2 are essentially the exact same thing, except the X and Y axis have been turned. So if you look at 1 and 2, right, F1 and F2 are both in the X direction, and they're equal, but they can be equal but opposite. So there can be forces in F1 and F2. However, neither F1 or F2, it's completely in the X direction. In the Y direction, you have F3 and only F3. So if that point is at equilibrium, F3 has to be a zero force member for both 1 and for 2. If you look at number 3, right, we've got F1 going completely in the Y direction, and you got F2 going completely in the X direction. Nothing offsets those. So again, for that point to be in equilibrium, or that joint to be in equilibrium, F1 and F2 must be 0. 4 is a little bit more difficult to see, right? In F2, there's only an X component. F1 does have an X component, and it has a Y component, right? There's no Y component to offset it, and the X component would actually be adding to F2 the way it's drawn. So those, again, they both have to be zero force members because that joint, that point, is in equilibrium. So if you look at the original drawing, you'll find that LB and HF are corresponding to each other on both sides of the truss. They're both a number 1 from my previous slide, zero force member. LC and HE are number 2. Again, it's just turning the X and Y axis in those. So those are zero force members. So you can remove those from the drawing. So now we're going to jump into the joints, and we are going to start solving. So we can start anywhere where there are 2 or 1 unknowns. Right, so at joint A, there's a 20 kilonewton load. That is the reaction force from the AY reaction force. And AL and AB are unknown. And the angle isn't given to us, but the size was given to us. And if you notice, both sides of the triangle are 2 meters. So since both sides are 2, the angle must be 45 degrees in there. So I can write a equation for summing the forces in the X, summing the forces in the Y. In the Y direction, I'll only have AL. I can solve for the AL force, plug that back into the X, and voila, I have my AB force. Now those will be the same as, right? AB is the same as FG, and AL is the same as HG or GH, whichever way you want to call that one. So point C. Point C, right? The AB is the same force as BC. So we got that 20 kilonewtons there. The 10 kilonewtons is the load that's applied at point C. So just by looking at this, we can identify that CK must be 10 kilonewtons and CD must be 20 kilonewtons. And again, we didn't do any math at all. We already had those two forces given, so the other two forces fall out. Now again, that's the same as point E on the other side of the diagram, or on the other side of the truss. Point K is up at the top, right? Point K is going to be identical to point I. So here we know LK because we solved for AL, and we now know let's see, that's KC because we just solved for that. We don't know KD and we don't know KJ. I assume them to both be in tension when I did the problem. And you can see I wrote my two equations, some of the forces in the X, some of the forces in the Y. I got in both cases two equations with two unknowns. So because of that, I had to solve the simultaneous equations. Notice both my answers came out as negative. So that means instead of them being in tension, they are in compression. That's all it means. And again, that is the same results as we get for I. So we're getting to the end here. So the last piece we need is this JD member, right? That's the one that's unique. It bisects the truss and gives us our symmetry on both sides. So we know we just solved for KJ. IJ is the same as KJ because of the symmetry. So because we know those two, right, we can sum the forces in the Y direction because we could sum the forces in the X direction too, but it doesn't get us any closer to the last unknown of JD in this case. So we can sum the forces in the Y direction. We know KJ, we know IJ, we can plug those values in, and we can solve for JD. So the last thing that's usually helpful, and actually I usually do this along the way here, right? Create a table of all the members and then fill in the forces as you do the calculations. And lo and behold, you'll see at this point, we have completed the table, and there you go. There is an example of applying method of joints from chapter 6 to a truss.